Okay, so let's get started with Chapter 7, which is quantitative composition of compounds. So basically what we're going to do in this chapter is learn about how to use the relationships from chemical equations to solve quantitative problems. So let's get started. So this is an outline of the chapter. These are various topics that we're going to go over and different types of problems that we're going to learn how to solve. So we're going to learn about this concept of moles, which is a very important concept in chemistry. And we're going to learn how to use that concept to calculate the molar mass of compounds. And then we're going to use those two topics in combination to figure out chemical formulas and how to work with those. So let's get started. So let's define this quantity of a mole. So an individual atom is very small, and they're teeny tiny, and they have this very small mass. So it's actually more convenient to use units that are existing on the macro scale. So instead of counting every atom in a chemical reaction, it's more convenient to work with groups of atoms. So an analogy that people use a lot is fruit in a supermarket. So sometimes instead of just counting the fruit, you take a bunch of the fruit and you weigh it, and you're charged by the mass. So if you know the average mass of a piece of fruit, you can kind of calculate the number of pieces of fruit indirectly. So let's look at an example here. So for example, if you know that an orange has a mass of about 186 grams, then it's asking you what mass do 75 oranges have. So 75 oranges times 186 is this 13.95 kilograms. So if you went to the supermarket and you wanted to buy 75 oranges for some reason, instead of counting all of them, you could just weigh out 13.95 kilograms and you'd end up with 75. So chemists kind of use this logic to count atoms. So they look at their weight, and then from that they're able to back out how many atoms are in the reaction. So let's talk about some other units of measurements where you measure things in groups. So you usually measure eggs by the dozen, or a half dozen, but typically this is the most common one, right? You always buy a dozen of eggs, and everyone knows that dozen means 12. Paper can be measured by reams, so if you buy a package of paper in a ream, you know that there are 500 sheets in it. And pencils can be measured by a gross, so 144 means a gross. So these are just numbers that have standard kind of definitions, and that's basically what a mole is too. So this is a standard unit of measurement for chemistry, and anytime somebody says the word mole, you know that it means this special number. So it's 6.022 times 10 to the 23, objects, and this can be atoms, molecules, eggs, anything. So you can have a mole of anything. But just note that it's a really, really big number, and that's why we use it to describe atoms. So 10 to the 23 is a lot. So this number is also called Avogadro's number. And like I said, it's useful because we don't want to count individual atoms in a reaction because there's, of order 10 to the 23 of them. So once again, the analogy is that 1 dozen, anytime someone says the word a dozen, we know that it means 12. Anytime somebody says mole, we know that it means this number of objects. So this really big number. So these moles can be used to describe elements, particles, or compounds, or basically anything, but they're usually used for these very small objects in chemistry, like electrons or atoms. And it can also be used as a conversion factor. So we can always change the number of atoms that we have into moles or vice versa, and it just gives us more convenient quantities to work with. Like I said, I'll always give you this on an equation sheet, but just know that this number of moles is this number that's of order 10 to the 23. So the next question we can ask ourselves is, how does this mole relate to the mass of the elements? The answer is that an atomic mass of 1 mole of any element is defined by the standard of comparing to carbon-12. So we didn't talk about isotopes yet, but we will in a few slides. So, the amount of substance that contains the same number of particles is exactly 12 grams of carbon-12. So basically, someone took 12 grams of carbon-12, counted the number of molecules there, and said, hey, that's the atomic mass of 1 mole. So 1 mole of any element contains the same number of atoms. So like I said, it's always this number 6.02 times 10 to the 23, but the mass of that can vary, obviously. So the example they're showing here is that if you had 12 quarters, would it weigh the same as 12 dimes? And the answer, of course, not is no. Quarters are a lot bigger, and they're made of something completely different, so the weight would be different. And this is true for atoms as well. So an atom of, or a mole of hydrogen would weigh, a different amount than a mole of helium, or a mole of xenon, or a mole of anything, actually. So these numbers are unique.